Okay. All right, so if I want to find the value of the car 1 year after purchase, how can I use the idea of exponential growth to get that? Alex, how can I use the idea of exponential growth to get this value right here? The value of the car 1 year after purchase.
You would have to multiply by 14.5%, which you have to turn to decimal. So the growth factor, pretty much.
You want to multiply by the decay factor.
Yeah.
And what is the decay factor?
A 1.14.
So you want to multiply by 1.145. What do we think of that?
That's the
Justin?
You have to put the percent into decimals and subtract it from 1.
Okay, so
And then multiply by that.
did you get a different decay factor?
Yes, I got 0.855.
0.855. Is that what you want to multiply by?
Yeah.
Alex, is that, what do you think? Is that better?
Yeah.
Yeah.
Actually, what I wrote down.
Okay. All right, yeah, so it's decay, so we need to get the percent that we keep. And the percent that we keep is 85.5% that we keep, so that decay factor is 0.855. And so when I do that, so equals that above times, did you guys get this price for the car? Or the value, right? Okay, and then what about 1 year later? Brooke, what could we do to get the value now, and after 2 years? Take that new value and multiply by 0.855. All right, so how do things grow or shrink exponentially? What's the key, right? This is how we started out the whole unit. We said, what exactly is the mechanics of exponential growth or decay? What is it about? Audie?
It's multiplication of one factor several times.
Right, in this case the factor is?
0.85.
Yeah, we keep repeating to multiply by 0.855 every time. That's the very specific way that something grows or decays exponentially. In this case, decay. We're always taking a portion of what we had before, right? Okay, so this should be easy. V of x, what is the percent change? What is the percent change? Fuda? That's what they gave us, right? But we want minus because it's percent change. It's exactly what they told us, that it goes down 14.5% every year. Okay? And we got the decay factor, 0.855. What about Vx? Shola, did you get that? This is what I heard. Like that? What do we think of that function? Okay, so that's all review. Okay, that's all review. Okay, so now the 5-year decay factor. So how did you find the 5-year decay factor? Omar?
It's the original decay factor powered 35. So up to the power of 5.
Can you explain why?
It's because of 5 years. They have to multiply 5 times by 0.85
Good.
times 0.855 times.
Right?
To give you the exact amount in 5 years.
That's right. So if we want one single multiplier that will advance us, is it 5 units of input or output? When we say the 5-year, we want to advance 5 units, or in this case 5 years, and that's input, right? That's the advance in the input. But the decay factor is the multiplier on which? It's output. So we want the one multiplier on output that will give us the next output for an advance of 5 input units. And so to get that, he said, well, it's the same thing as multiplying by 0.855 1, 2, 3, 4, 5 times. So it's equivalent to
0.4560.
1, so it's one whole factor that would take us all the way, for instance, from 0, the value at 0 years, to the value at 5 years. And so the equivalent number is what he said, 0.855 to the 5th, right? Because we see it in blue there. We're multiplying by that decay factor 5 times. So to do it all at once would just be to the 5th. And you got, what'd you get, Omar?
0.4569.
Okay, so what is the 5-year percent change? Christian?
5 years.
So here we got our 5-year decay factor.
I have a minus 54 points.
And how'd you get that?
I took 1 and subtracted the growth factor, or the decay factor we have right now.
Okay.
And then that would give you your percent change.
Yeah, because our decay factor, what is the meaning of that number? What's the meaning of that 5-year decay factor?
Amount of heat.
The amount of the value that's held, remains, right? 45.7% of the value of the car remains after 5 years. Therefore, how much was lost? 100 minus that, right? 100 minus that, so that's the negative 54.3% is the percent change for 5 years. Okay, so now if we wanted to write a function, now instead of the number of years, the number of 5-year periods, Wn. Patrick, did you get that?
It would be Wn equals 25,000 times 0.457 to the power of x.
What do you think about that? Does it work? Yeah, so whatever unit that is, you have to have the same decay or growth factor that you're raising it. So this is n is the number of 5-year periods. So we need a 5-year decay or growth factor in the parentheses. Okay? Anyone do it a different way?
Wait, I have a question.
Yeah, sure.
That's question 4, right?
Yeah.
Okay. 0.457 is the 5-year period decay factor.
That's right, exactly.
But if you do that, wouldn't you get the straight away the 5-year period instead of and for example, if you use this and then add 1 or 2, you would get 5 times 2. See what I mean? Right.
Are you suggesting that n equals 2?
Yeah, I mean, and in this case, if you want to find the 5-year period, it would be 1 straight.
N would be 1.
Yes.
So we would have 25,000 times 0.457 to the 1.
That's for 5-year period.
1 5-year period.
Yes.
Would it work?
That would work for 5-year period.
Okay. So what if n equals 2?
That would work for 10-year period.
Right. So this is n is the number of n is always the number of 5-year periods. That's what we're defining n as.
Oh, okay.
Yeah, it has to be, right? So that's how n is defined.
I understand.
Yeah. Okay. So would anyone do this a different way? Set up this w function a different way? Yeah. Go ahead.
You could have 25,000 times your original growth factor, 0.855 to the 5n.
That's what I did.
Okay. So here's our original growth factor, and he wants to raise it to the 5n. Does it work?
Yes. Yes.
How can we convince ourselves? Let's try some different values of n. Oh, go ahead.
Because n is going to be your number of 5-unit changes.
Okay.
So if you have one 5-unit change,
Yep.
and you put in 1, that will give you your 5-unit change.
So he's saying if n equals 1, we end up taking 0.855 to which power if n equals 1? The 5th, right? And that's what we want. If n equals 1, then we want to multiply 0.855 together 5 times. And that's what we get. What if n equals 3?
15.
So we get 15 here. And if we want 3 5-year periods, how many 0.855 should that be multiplied together? It should be 15, so it works. So that's another way to do it. So you can write this function in terms of the 5-year decay factor or the 1-year decay factor by adjusting that exponent there to be 5n. That works good. Okay, so now I want to find the value of the car after 9 years. And I want to do this in an efficient way, and I want to use the 5-year decay factor. So this number, 0.457. How could I use the 5-year decay factor to find the value, this really gets to see if you understand what the 5-year decay factor is. I want to find the value of the car after 9 years. Anybody? Jared, did you have an idea about this? Okay, so A is the key. Aaron?
Would it be 25,000 times 0.457 to the power of 1.8?
Okay, it sounds like you're using the function. I don't want you to use the function. I just want to use the 5-year decay factor to get what it would be 6, 7, 8, 9. We kept going 6, 7, 8, year 9. What would the value be in year 9? Just by using 5-year decay factor. I know Christian knows. Anybody? Does the 5-year decay factor only work on the initial value? Does it only work on the initial value then to find the value 5 years later? So if we wanted to find the value at 9, how could we use the 5-year decay factor? Nina?
You would take the value of the car after 4 years,
Okay.
and then you would multiply that by 5-year decay.
Would that work? So we took the value at 4 years and multiplied by the 5-year decay factor. It's going to give us the value of the car 5 years later, or in other words, in year 9. Yeah, that's it. So I could take, what was that? This 13,3599.4. Shit. The value at 4 and multiply it by 0.457. And that will give me the value of the car 5 years later, or in other words, in year 9.
I found a different.
Okay, was it
It would be
as easy as this? Was it as efficient as this?
No.
Yeah, so I'm really focusing on the meaning of the 5-year decay factor. Okay, so now I want you to take a moment and maybe think about how can you use, in the same way, use the 5-year decay factor to find the value of the car at 13 years. Okay, in the same way, how could you use the 5-year decay factor to find the value of the car at 13 years? Go, see if you can do it. I'll finish attendance. So I want to use that 5-year decay factor now to find the value of the car at year 13. How could you do that?
You could divide, use the one we set up before and use the exponent of 2.6, since that times 2.6 times 5 is equal to
Okay, maybe, but I just want to use the straight up 5-year decay factor. So maybe that would work. Jaden?
Could you use the second year of the v function? Or sorry, the third year of the v function? So the value is y by the third year. And then times it by 0.457 to the second power.
Okay, so you want to look at this value of the car after 3 years?
Yeah.
And you want to multiply it by the 5-year decay factor twice. What do you think? Yeah, exactly right. You start with the 3-year value. If you multiply by the 5-year decay factor, that will give you what? The value after? Well, just once. 8 years. And then you take the 8-year value of the car and multiply it by the 5-year decay factor again. It'll give you 13-year value, right? 13-year value. So you could take this one right here times the 5-year decay factor twice. Okay, so V of x. So using V of x, what's the value of the car after 9 years? Using V of x. So easy, right? How could you just represent it? What would that be? Yeah, Fuda. Uh-huh. Yep. And that is, how can we represent that with function notation?
V of 9.
V of 9. Oh, V of 9. V of 9. That's that value, and it just means plug 9 into the function, which will multiply the 0.855 together 9 times. Similarly, V of 13. Okay, so skip that question. So let's summarize what a C unit, so C unit, any unit, like any number of years in this situation, or C unit growth factor. Could you finish this statement? A C unit growth factor is what? What is that? See if you can write your own definition for this. Do you just kind of have a vague, nebulous idea of what it is, or can you articulate it well? That's what we want. We want you to be able to articulate this well. Exactly what is a C unit growth vector? Brian, what do you think?
It's the growth factor for the change of C years.
Well, what's a growth factor? So you can't use growth factor to define a growth factor. So what is a growth factor? Multiplier. Multiplier. This is the multiplier. That's what these growth factors are. They're multipliers. What kind of multiplier is it? What's that? He's suggesting it's a multiplier on the output. What do you think? Yes. Is a multiplier on the output? Who can take it from there? Anyone? Yeah?
For any given change in the input of C.
Okay, so it's going to, okay, let's put that at the end. So for a change of input, put that at the end, for a change of input of what? C units. So what are we missing in the middle? Justin?
Of the preceding term to get the next term.
Well, so instead of next term, so that's what we're saying for a change of input is C output. So it's a multiplier on output to give us what? Watch out. So now watch out for next, because next kind of has the idea of what? 1 unit change, right? It's saying next. Now that has the implication that you're gonna make the input just increase by 1. So we don't want to use next anymore. Okay? So it's multiplier and output to get a new output. And which output? For a change of an input of C units. Okay? So it's a multiplier on the output to get the new output for a change of input of C units. Okay, really important that you can, so this will be next week's quiz, will be you writing out this definitions so that when you're working problems, you're always reminding yourself, what is this number? What does it mean? Okay. Let's try this next example here. Okay, so we've got initial mass of 50 in a Petri dish. It's doubling every 7 minutes. We want to complete the table. And so here's kind of a new situation. So if it's doubling every 7 minutes, and so we know this is all about growth and decay factors. So as soon as we can in any given problem, we want to get a growth or decay factor to hold on to. So can we come up with some growth? This is growth here. Can we come up with some growth factor right off the bat that would get us started? Jared Smith.
Sorry, what was the question?
So can we take this, so exponential growth is all about growth factors. That's the centerpiece. If we can get growth factors, we do all kinds of things. So given the situation, can we come up with a growth factor right off the bat? An initial mass of 50 doubles every 7 minutes. So can we get a growth factor? He wants the 7-minute growth factor to be 2. What do you think? Yeah, that's it. So this means that doubling every 7 minutes means our 7 minute growth factor is 2. Right? Because it's the multiplier on the output to get the new output 7 minutes later. All right, so does that give us any values in the table right off the bat? After 7 minutes, we know that we have? And what about after 14 minutes? All right, so we've got this 7-minute growth factor is 2. It's doubling. But what we'd really like is the 1-minute growth factor. So what is the 1-minute growth factor? Any ideas? Audience?
Well, if you had if the exponent, the multiplier was 7 over 7 to give you the period of 7 minutes, then you have 50, and then since you're doubling it, it'd be times 2, and then that exponent 7 over 7 is just 1. So that would give you that. And then, so any numerator in that fraction would give you the right total multiplier to get the new mass. So for the 1 unit, I think you just put the initial mass 50 times 2, and then the multiplier would be whatever fraction of that period you're trying to get. So like 50 times 2 to the 1 over 7.
Okay. Okay, good ideas here. So what were you going to say, Nadine? What's that? You were stretching. Okay. All right, so let's see if so he's come up with a theory. Let's check and see if his theory is right. Let's call the 1-minute growth factor we're going to call it, since we don't know what it is, we're going to call it B, right? Because that was consistent. We said A, B to the X was our exponential form, right? Where B was the 1-unit growth factor. So let's call it B. And so if the 1-minute growth factor is B, how can I use that to express the mass of the bacteria 1 minute after this initial amount? How can I use that 1-minute growth factor of B to express what the mass would be after 1 minute? Jonathan, what do you think?
What was that?
So how can you express, so if the 1-minute growth factor is B and we start with 50, how can I use this 1-minute growth factor to express the mass of the bacteria after 1 minute? So we got 50, we got the 1-minute growth factor is B, so what will the output be 1 minute later after it's 50? That's what we're asking. Not sure, Tim, do you know? Okay, what is this number of B? What is it? How much? Okay, so what would it be? What would the mass be? 50B? 50B. It's 50B, right? That's what the 1-minute growth factor does. It's the multiplier on the output to give you the next output. It's the multiplier on the output to give you the next output. So you're going to make 50 times B. All right, so what about after 2? How much mass would we have after 2 minutes? 50 B squared, right? We multiply by B again. This is the same thing we've done before. Okay, so every minute we multiply by B to get the mass 1 minute later. Just keep doing it. The 1-minute growth factor. We're trying to figure it out. We don't know what it is. So we're using the symbol B to stand for it as a way to figure out what the value is. We know that the 7-minute growth factor is 2. But we don't know what the 1-minute growth factor is. So we're just going to call it B and do the math using B. Is it fair? So now so what happens here? When we multiply by B, how many times to get from 50 to 100? 7 times. I think I only drew 6 there. So we multiply by b 7 times, and that has the result of multiplying by what? What? It's b to the 7th, and b to the 7th has the effect of multiplying by what? 2, right? Because we said the 7-minute growth factor is 2. To get from 50 to 100, you multiply by 2. But another way you can do that is multiply by b 7 times. Do you see it? So b to the 7th equals 2. B to the 7th equals 2. This is key. You can construct this too. All right? So then that allows us to solve for b. How do we solve for b? Take both sides to the 7th root, 1/7 power. Okay?
I did it a lot easier than that. Through a different method. I just put to the 1/7 and solved.
But that's assuming you knew what it was. We didn't know what it was.
But I took 50 times 2 to the 1/7. And that gave me my 1 unit growth factor.
But how did you know it was 2 to the 1/7? How did you know that? We didn't know that.
The information was later. I'm confused when you have it.
No, we knew that it doubled every 7 minutes. We didn't know anything about 2 to the 1/7.
Well, if it doubles 7 minutes, then 1/7 of that minute is 1 minute. And I got the right answer because I checked it.
Right, but it's not. You may be familiar with it because you saw it last. You saw it before, but we have to mathematically show what happened. We can't. You kind of assumed that it was true, and then you checked and found that it was right.
I didn't know it was true. I just kind of thought that would give me the right answer.
Right. That's exactly what I'm saying. It was a very good guess, an educated guess. Okay, but mathematics is about proving it, and showing it. Anyway, deriving it precisely. Okay, so. But this should make sense. You should be able to do this. You should be able to reason that if we multiply by b 7 times, that's equivalent to multiplying by 2 once because of what's given in the problem. And therefore, to solve for b, you're going to take the 1/7 root of 2. Okay, so, yeah, go ahead.
I'm confused about b to the 7 equals 2. Doesn't it equal to 100? Then how come it's equals to 2?
What is b? It's the 1-minute growth factor, right? So that's the multiplier on the output to get the next output. So I'm showing you that if you kept multiplying by b 7 times, then that would advance you 7 units of input, right? It'll give you the output 7 units later. Well, we know that that's 2. That's the 7-minute growth factor. That's 2. So when you multiply by b 7 times, that takes you from 50 to 100. But that's what 2 does. Is that better? Okay, so there's our 1-minute growth factor. So I want you to find the 1-minute percent change. I'll put some questions in here. Find the 4-minute growth factor and percent change. Go. And then find the mass at 11 minutes, elapsed time using a growth factor. Let's make that 18. How about 18? I'm going to change that to 18. Do them both if you want. If you already did 11, do 18. Find the mass at 18 minutes using a growth factor. Question? Multiply growth factors together. Remember, growth factors will multiply our output to get another output. We'll give you the output at 6 minutes. Multiply by the 4-minute growth factor, we'll give you the output. Okay. Yeah, that'll work. There's an easier way. You just don't have to multiply it. You don't have to use the power of 4. Just use any power to get mass at 18 minutes. Just use the 4-minute growth factor one time. What would you just do that? What? Yeah, I'll go to 14. Okay. Joe, were you able to get the 1-minute percent change? How'd you get it? Two raised to 1/7. So that's our 1-minute growth factor. So what's the percent change? The 1-minute percent change. 10.4%, right? So for the first one, you should have gotten that the growth factor 2 to the 1/7 is 1.104 for a percent change of 10.4%. Don't like that. Okay, so how about the 4-minute growth factor? How did you find the 4-minute growth factor? Morgan, did you get that?
Yeah.
What'd you do? Okay, yeah. So did you fill in this table?
Yeah.
So if we made this table, we know that we've got, this is equal to 50, or the previous entry times what? Right, that's our 2, that's right, 2 to the 107, to 1/7. Okay, so those are our spreadsheet.
Cool.
Never seen a spreadsheet before? Yeah, so you can just grab on, you can just repeat. You grab in the corner, there's a little black plus comes up, and you just pull down, it repeats the same formula. Okay. So tell me again, Morgan, what you do.
I use the output of 4 and divided it by the output of 0.
She took 74.3 divided by 50. Will that give it a 4-minute growth factor? Yeah, that's a good way to do it. Is there another way to do it? Can we get it from the 1-minute growth factor? Instead of from outputs? Anna? Yeah, so it's just like multiplying that thing together 4 times. So we just take it to the 4th. So we can do that 2 to the 1/7 to the 4th, or 2 to the 4/7. And when we do that, what do we get? What do you get for that 4-minute? Anyone got a decimal approximation for the 4-minute growth? 489? 48. Which gives us a percent increase of 48.6? Why do that? I have to do that. Okay, so that's the 4-minute growth factor and percent change. All right, so how can we use a growth factor to find the mass at 18 minutes? Here's the key question. So Taz, did you get that? So can we very simply find the mass at 18 minutes using a growth factor?
I used to, I used 4 minutes and then that's 7. Is that right?
How about just the 4-minute? You can do it with just the 4-minute. How can you do it?
Take the 14 minute, so 200 times the 4 minute.
He wants 200 times the 4-minute growth factor. That's it. You take the output at 14. If you multiply it by the 4-minute growth factor, this 2 to the 4/7, it will give you the mass 4 minutes later or at 18 minutes. So I'll write that out. We're going to take 200, which is, we didn't really make a function, but let's say f of what, 14 times the 4-minute growth factor. And that'll give us the new output 4 minutes after 14 minutes or at 18 minutes. So it equals f of 18. So this is a great thing because it uses function notation and also kind of embodies the idea of exponential growth, that we're multiplying by a growth factor to take us from one output to another output. In this case, 4 units later. Okay, so can we write a function, say g, that gives, so g of n, such that n is the number of 10-minute periods. So n is the number of 10-minute periods, and so g of n will give us the mass for n, if n is the number of 10-minute periods. Go. So we start with the initial amount, 50. Oh, do you want to do it?
Yeah, I just want to make sure something. So if I was like too lazy to go to the calculator and get the change over to 10 minutes, can I just put the 1 minute and then have it 10 and
Yeah, let's use exponents, yeah. So what's going to be in the parentheses? Tell me.
that's the 1 unit, the 1 minute growth factor,
Right.
which is 1.104.
2 to the 1/7. Is that it? N is the number of 10-minute periods?
Oh, no, and then you need a 10
Right.
for the actual.
That thing to the 10. So if you take 2 to the 1/7 to the 10, you get the 10-minute growth factor. And so then if n is the number of 10-minute periods, we're set, because however time, whatever n is, will be the number of times we multiply by the 10-minute growth factor. Okay, anybody have a question? Please.
Shouldn't you simplify that 2 to the 1 over 7 times to the power of 10 and just combine that 10 and the 1/7 to 10 over 7?
Yep, you can. So what he's saying is, can we multiply exponents here? Yes. 2 to the 10 sevenths. Is that what you're saying? Yeah. 2 to the 10 sevenths. What does that represent? What number is that? 2 to the 10 sevenths.
10 minutes.
The 10-minute growth factor, right? So the 10-minute growth factor, it says n is 10-minute periods. So whatever growth factor you have in this parentheses has to match whatever your input is, right? Your input is 10 minutes, so you want the 10-minute growth factor inside there. And so I just separated it out to show the 1 and the 10. But yes, you can do 2 to the 10 sevenths. Absolutely. Okay, questions on this example? Okay, so let's keep going. This says that this has all the answers. Okay, this says that the body removes 85% of the ibuprofen present in the bloodstream every 5 hours. So we're going to take 500 milligrams of ibuprofen, and it removes 85% every 5 hours. So we want n is the number of 5-hour periods since taking the medicine. T is the number of hours since taking the medicine, and m is the number of minutes since taking the medicine. So I want you to start by, actually, before anything else, I want you to practice deriving this. So derive the 1-hour decay factor and use it to fill in the table. Okay, and that's number 1. And then here's 2, and 3, and 4. Okay, this is kind of putting it all together now. Okay, so there's lots going on here. Take your time. Check either with Megan or I or someone around you before you press on to the next question. Make sure you understand what's going on. Okay? I want you to actually derive it from scratch, the way we did it in the last example. Find that 1-hour decay factor. We'll call it B. So call it B to start, and then derive it using this reasoning that we used before.
use, one consecutive to
Okay, let's actually start with number 2 because that's kind of the easier place to start. And then number 3 will take us back to number 1. So number 2, the f of n function. Jacob, did you get that?
F of n equals 500 times 0.15 to the power of n.
This is what he's offering up. Christian likes it. If we've got so what are you saying 0.15 is, Jacob? What is the number 0.15? What does that mean?
The decay factor.
For?
The amount of ibuprofen in the body every 5 hours.
It's the 5-hour decay factor, right? And so if n is the number of 5-hour periods, then that matches up with our decay factor, right? So 0.15 to the n. Okay, so now we got the 5-hour decay factor is 0.15. And so how can we use that to get, if we're going to do g of t, we need the 1-hour decay factor. So how can we figure out what the 1-hour decay factor is? Jared?
So the one would be 500 times 0.15 to the fifth, which equals that to 0.0379. And that's what gives it the fifth equal.
I want to, yeah, that's right. I want to derive that 1-hour decay factor, though. How can I actually derive that from scratch instead of just assuming what it is? Diana, do you know?
No.
Okay. Nadine,
Either have 500 b to the 5,
right?
b to the 5 is equal to 0.15.
Okay, right. So here's this thing again. Look, so multiplying by b 5 times is the same as multiplying by what once? 0.15. This is the key right here. Got to see this. So multiplying by b 5 times together is the same as multiplying by 0.15. So, therefore, because b to the 5th, there's our b to the 5th is our 0.15. And so you want the 5th root of 0.15. Okay, so now we're going, so you wanted to tell me what the function was, Jared. Does that agree with what you did for the 1 unit? 0.15 to the 1/5?
Yeah.
So what will it be?
G of t equals 500.
Yep.
0.15 to the 1/5. To the
Is that what you said? Okay, so there we got it. And so notice that we could also write this as 0.15 to the what? Yeah, t over 5. Okay, so when you see it like that, 0.15 to the t over 5, what is the 0.15? That's the 5-unit growth factor. Because when t reaches 5, then we want to multiply by that thing once. We'll multiply that thing once, right? When t is 5, we'll multiply that by that once, so that must be the 5-unit growth factor. And when t is 20, we'll be multiplying by that how many times? When t is 20? 4. So therefore, if we're multiplying by that thing 4 times, and t is 20, then that must be the 5-hour growth factor. All right, so how do we get the 5-hour percent change? see. Muhammad, did you get that? So where can we get it from? Where does the 1 hour percent change come from? The 1 hour percent change comes from? Patrick, where does that come from?
The 1 hour?
Yep.
It's our 5 hour percent change, or sorry, no, our 1 hour growth factor we find out.
Okay.
Get that by doing 1.5 to the power 1/5.
I got 0.684.
And then we do 100 minus that.
100 minus 68.4. So what'd you get? 31.6?
Yeah.
So the 0.684, what is that? That's the, what number is that?
1 hour.
1 hour multiplier, right? Decay factor. Okay, so now what about the one, if the 1 hour decay factor is 0.684 or 0.15 to the 1/5, what is the 1 minute decay factor? Christina, did you get that? No, it doesn't work to divide by 60. Then you're assuming constant rate of change. If you divide it by 60, you're saying you get the same amount of change each minute. So instead we want, what do we want instead? Brooke, did you get that? The 1 minute.
Would you multiply or raise the exponent 0.15
Okay, so she wants to take, I'll write this out here. She wants to take the 0.15 to the 1/5, and that's the, which decay factor is that? That's the 1 hour. So to get the 1 minute, raise it to the 1/60th. Does it work?
Yes.
Yeah, because we're asking what number multiplied together 60 times is going to give us this, our 1 minute decay factor. So what number multiplied together 60 times will give us the 1 minute decay factor, and that's this number to the 1/60th. Okay, so then our initial amount is 500. And so we can take that whole thing as the 1 minute, take it to the M for the number of minutes. So notice how many decay factors we have all wrapped up in this one decay factor. 0.015, which decay factor was that? 5 hour to the 1/5. 1 hour to the 1/60th. 1 minute. And then in fact this whole thing is another decay factor. It's the M minute decay factor, right? So to the M gives you the decay factor for M minutes. Okay? Find the 1 minute percent change. The 1 minute percent change. Yeah, question? Thank you. Good point. If it asks for percent change, he's right. If it asks for percent change, we gotta make that negative. Okay, find the 1 minute percent change. I did not say put your books away. I said find the 1 minute percent change.
Raise it to the 1/60th, is that going to be a second?
Yeah, if you did that again, the 1/60th. Yep. Okay, so let's see. Did you get it? Shola, did you get it? So what did you do to get this 1 minute percent change? Okay, so the growth factor is, let's take our 0.684. What was that? 0.684 to the 1/60th? Did you get that? Is that the 1 minute decay factor? Did you get that? Somebody else? And so what is the percent change?
Actually, 1 minus that multiplied by 100.
Right, exactly. And then you get equals 100 times 1 minus that. 0.63%. Is that right?
Yeah.
0.63% that goes down every minute. Okay, so for Thursday, you're preparing for the quiz if you have Thursday recitation, and then it's just written homework. Webwork's on pause at the moment. So there's a written homework assignment, and it's not short. Start it tonight, okay? So just written homework for Thursday plus the quiz.